Alright, so let's think about the operational semantics of the lambda calculus, or this simply typed version. So one of the things we've done in the previous chapters is we've incorporated the notion of a value into our semantics, so we can sort of talk about things like terms evaluate to values and so on and so forth. So we'll start off with that here as well. So for the symptic type lambda calculus, we've got a few different terms, so we can consider which ones of those should be regarded as values. So true and false makes sense because they're sort of basic Boolean things. So they'll be values. If expressions won't be values, because we want to always sort of keep evaluating if we don't want to sort of stop at the point where we have an if that's unevaluated. Applications are not values because they are really representing the application of a function to some arguments, and we clearly want to keep doing work in that situation. There's an issue with abstractions though. There's basically two design points, and different languages make different decisions on what to do with abstractions. So if we have an abstraction like this, which is saying that we've got an argument x of type t and the body is t1, we can basically split the decision about whether we bother to evaluate t1 or not. And if we do, then we essentially keep reducing the body of the function until it becomes a value, or becomes something like a value. One of the issues there is that you can't always evaluate the body fully, of course, because some of, and for most functions, the value of the body will depend on the value of the argument. And at this level, we might not actually have the argument value at this time. For example, it might be a function that never actually gets applied to anything, so we don't know what the argument would be. Right? The value of a whole program could be a function that's unevaluated, unapplied. So that's one possibility. The other possibility is to say, well, we don't care what T1 is, we just leave it unchanged, and we just say that every abstraction is a value. And so if we get a reduction sequence that gets to an abstraction, we just stop at that point. We don't keep going in that point. So different languages make different choices in this regard. So in COC, actually, they make the first choice. So they will do things like, in this case, evaluate the body of this function to get 7. And one reason why they can do that in COC is that they have a sort of stronger notion of evaluation that helps things where it sort of makes sense to evaluate things that might have variables in them that don't have values yet. So an example would be if I had this, you might say, well, actually, maybe I'll do it the other way around just to be a bit more precise. We might say this, and COC will be quite happy to probably evaluate that to 7 plus x, because the plus can make some progress on working out the 3 plus 4, but it has to stop when it gets to the point where it's got 7 plus x, because it doesn't know what x is. So we've seen plenty of examples of that sort of thing in the course to date, where we've done simplifications of terms that have variables in them, and the system will simplify as much as possible, but if it gets to a point where it needs the value of a variable and it doesn't know it, it will stop the evaluation. And this is less of a useful thing for real programming languages that aren't sort of designed for proof sort of purposes. So most mainstream sort of functional languagey sort of things don't bother doing that, because they're essentially not set out to, most evaluation mechanisms for real languages are not set out to sort of do evaluation for programs that have unspecified variables in them. Often you want to basically say, well, I'm not going to do the reduction inside a function until I actually apply it to something, because I might never need the body to be evaluated. And that's a common choice for even object-oriented languages. You don't evaluate the body of a method until you call the method. So that's the decision we'll make here as well. So we can define values to be the Boolean the two booleans and any abstraction. So this is analogous to the definitions we've had before for the language, for example. Okay, so then we sort of need to think about what sort of programs we're willing to try to evaluate. And a sensible choice is to say, well, it doesn't really make sense to evaluate a program that has some unspecified variables in it. Right? So if I said we want to evaluate the program x plus 1, Coq would probably say, well, that's just x plus 1. But in a programming language context, it doesn't really make sense because we don't know what the value of x is, so we can't evaluate this. So a common choice for programming languages, and what we'll make here, is we say that we need to we don't want to be able to refer to any undefined variables. And a formal way of saying that is that the program is closed, which means it doesn't have free variables. So this x up here is known as a free variable, and we'll see how to define that in a minute. But we're basically saying this is not allowed. Okay, but I could, for example, have something like this, which is okay. So that will just evaluate to the same expression. So x is not free anymore because it's bound by the lambda expression. Or if we had numbers in our language, we could do something like this and say, well, let's apply that to 5, and then this would reduce to 6, for example. So this makes a difference because together with this idea of not reducing under abstractions, in other words, inside lambda expressions, we don't need to worry about whether variables are values, because always when we're doing our evaluation, we'll be working with closed terms. So the terms will always come from within the program. The variable values will always come from within the program, and will always be values in that sense. So that's why we don't have variables as one of the kinds of values in here. This decision of only working with closed programs also simplifies the next topic, which is substitution. So when we get around to defining what it means to execute the lambda calculus, the fundamental operation that we need to be able to do is apply functions to arguments. And ignoring booleans for the moment, that's the only way we can actually get anything done. Is we have some function, we have an argument, we somehow bring the argument value into the function body, and then we continue evaluating from that point. We need to be able to pass parameters to functions and continue evaluating. So the usual way that that's sort of defined in the lambda calculus is via a substitution operation. So if we have this function here that's got a single parameter x, which is a boolean, and the body refers to x a couple of times, and the actual parameter is false, then what we want to do in the evaluation is we want to take the false, we have to go and say, well, x is false, so we need to replace all the x's in the body with false, which gives us this term now. So the function application has been turned into an if, which is the bodies with the parameter value substituted in. And then obviously we can continue evaluating that in the normal sort of way for an if expression. Okay, so it fundamentally comes down to function application is realized semantically by substitution. So as long as we can do this substitution operation in a safe, correct way, then we can use it to implement the evaluation of applications. So here's a few examples, and one of the issues with substitution is it gets a bit tricky in various cases, which you'll see. And substitution is sort of the bane of programming language theorists' lives, in that they struggle with how to do it and getting it right, and maybe are there alternatives to do other things that would avoid substitution or make it easier. We're going to stick with the sort of basic substitution with a few caveats here. So this square bracket notation here is a fairly common one. There's a few others around, but basically this says we've got some term t, and it might have some x's in it, and we want to go through t and replace all the x's with s. Okay, and an important caveat is we only want to replace the free versions of x. We'll see what that means in a minute. So this here is saying, well, replace x with true in the term if x then x else false. So you get a true here, and the false stays as it is. If the term we're replacing in is just the use of the variable, then obviously we just get the replaced thing. This is very similar to the one up here, except there's a y here, which is not part of the substitution operation, so it just stays the same. And similarly, if the thing we're substituting in is a use of a variable that's not the variable we're substituting, then we just get the original variable back again. If there are no uses of the variable in the term, then we just get the term again. This one says we're substituting in a function. So again, we're turning x into true inside this lambda expression. So we can go inside the lambda expression and find the x and turn it into true. There's a crucial thing that's going on here, which is that the fact that this is lambda y is important. So we'll see that in the last example. These other examples are basically similar. So this is saying, well, the body is just x, so we replace the x with true. In this case, the body is y, so there are no x's in this term, so it stays the same. The last one is the trickiest one, and this is where lots of substitution things get into trouble. We're replacing x with true, but the aim is to replace just the free versions of x. Where there's another version of x in here, which is another variable entirely, which is bound by the lambda expression. So this x inside the lambda is referring to this x here. And we don't want to replace that x. As we'll see in the future, that if we did that, that would make the evaluation wrong. So in this case, we get back exactly the same term as we did. So there are no free x's in this term, so we just return the same one. So getting that right is the trickiest part of substitution and notoriously difficult in general for lots of functional languages. Okay, so we can define that operation informally like this. So we've got things like, if we're replacing a variable with that variable, then we get the thing we're replacing it by. Otherwise, if the variable is some other variable, then nothing happens. In a lambda, if the bound variable is the same as the one we're substituting, nothing happens, because we're not allowed to equate the two x's in this case. But if the bound variable is different, then we leave the bound variable in place, and we go inside the body and do the substitution on the body. For an application, we just do the substitution in the applied expression term and in the argument term. Substituting in true and false doesn't do anything because they don't have any variables in them, and substituting in an if just substitutes in each of the components of the if in turn. Okay, so the trickiest cases are the two that sort of have to make some determination about which variable it is we're dealing with here. And we can use the same techniques that we've used previously in the course to define a substitution function, which takes the three pieces, right? The x, the s, and the term that we're substituting, the t, and returns the substituted term. And this definition follows the informal version up here. It merges the two cases for variables into one case. So there's an if here that decides whether we're substituting the same variable or a different variable. And the two cases for abstraction get substituted, gets merged as well into this, again with a test to see whether we're substituting the same variable or a different variable. And the notation works nicely, so this is quite a readable definition. So it's pretty simple, not too much going on. The main issue that this is sort of glossing over is that if we do something like, imagine I did x is y in lambda y, or y, something like that, x like that. So what should this do? So one possibility is it should just replace the x with a y, so we get this. And this is wrong because the point of the substitution is to substitute x, but not to, we can't equate the y that we have on the outside of the term with the y that's on the inside of the term. For similar reasons to the substitution that we're just doing. We can't equate a variable on the outside with the one that's bound by the term. So this gives us the identity function, which is not the right answer. So probably what we would want to do in this case is rename the variable and do the substitution with the old name. So in this case we get the constant function that always returns y, which is what you'd expect if you've got this thing and you're changing the x into the y that's on the outside. You'd expect a constant function that returns this value, not this value. Okay, so this is tricky. Basically it means that you have to be very careful if the thing you're substituting in has free variables in it, because in this case the y that's on the outside is getting captured by the y on the inside, and that can happen in general for lots of different cases. So full definitions of substitution have to sort of deal with this case by doing something like this renaming operation. And fortunately in this language that we're defining here, we don't have to worry about that, because we're going to sort of define that we can only do substitution where the term in this position that's being substituted in doesn't have any free variables, right? And that works for this language because we're making this assumption that we're starting with closed terms, and every time we do an evaluation step we get another closed term, and we don't have to worry about free variables sort of magically appearing in the middle of our development. So this simplifies the question for us, but in general it's quite a tricky point. Okay, so this is substitution as a function, as a computational thing. In the homework you're asked to do this substitute exercise, which is here, which is to define the same substitution relation, substitution as a relation between terms, which we've seen before quite a few times for evaluation, for example. So you have to sort of extend the definition. They give you one of the cases here. You have to extend it to handle all the other cases of substitution. And then in the second homework exercise, substitute correct, you're asked to prove that the function one, which is this version, is equivalent to the relational one, which is that version. So you've done some proofs of that style before, but this is applying it to the substitution operation. Okay, so that's substitution. So we're almost at the point where we can actually write down what the evaluation rules are. So here they are. We'll start. The key thing that we care about evaluating things in is applications. So we're going to start with this one. And essentially, in a similar sort of way to what we've seen in the small step, so this is a small step semantics. We just want to do the minimal step to progress the evaluation at this stage. Just like in the small step chapter where we had a plus and we had two subterms in the plus and we evaluated the left one first until it became a value, and then we evaluated the right one until it became a value. That's exactly what we do here as well. So in this rule we're saying, well, if T1 can make a step to T1 prime, then the whole thing makes a step to T1 prime T2, or the argument stays the same. And if we get to the position here where the function part of it is a value, then we try to step the argument, and then we can step the whole thing to V1 T2 prime. And then hopefully at some point we get to the point where we have the left part is a function, i.e. a lambda expression, and the right part is a value of some kind. And in which case, so that's requiring this premise, in which case we implement it by just doing the substitution as we've defined above. Okay. Notice that this doesn't do anything for, well, values could be booleans, and if this thing evaluates to a boolean, then this rule doesn't apply, so we get stuck. So that's the case where type systems have to help us out by stopping us trying to evaluate programs that try to apply booleans as functions, things like that. So these rules are only dealing with the cases that work. Okay, so you can see the basic evaluation step, which is usually called beta reduction, amounts to just an application of the substitution operation. Okay. For booleans, we have to define some rules for if, and the usual story is, we start with this one, is we've got some if. We want to first evaluate the condition, so we try to step the condition, and then we just get the then and the else branch stay the same, but the condition has been evaluated a bit, and we keep doing that basically until the condition turns into either true or false, in which case we can then decide which branch to evaluate. So we either replace the whole if with T1 or with T2, depending on whether the condition is true or false. And again, this is assuming type correctness in some sense, right? So if T1 eventually evaluates to a function, then neither of these first two rules will apply, and we'll get stuck again because we can't do if on functions. Okay, so taking those simple rules, we can formalize them in the same sort of way as we have in the past. So we have one rule for each of the inference, one constructor for each of the inference rules above, and we're just encoding the form of the rule directly using the notations that we've already got. So I'll let you read through those on your own. They're pretty straightforward once you understand what the evaluation reduction rules are doing. Okay, we can also, as we did before, talk about the multi version of this. So if we string a bunch of single evaluation steps together, we want to sort of progress to a fully evaluated thing. So there's some examples here of taking bigger expressions or terms and evaluating them multiple steps to get to a value. So in this case, the value is a lambda. And the proof of that sort of stuff, they're using some aliases here just to make it a bit easier to write some of this stuff down. The proof of the evaluation here is very similar to what we did in the imp small step stuff, where we have to do multi-steps and decide at each point which rule to apply to make a thing, and it's almost always applying an abstraction in this language, and then at the end we can use the REFL to solve the final goal. So again, I'll let you have a look at the other examples here. They're all just exercising different aspects of evaluation to check that things are working right. It's not too important, but they show that you can use this normalized tactic, which they defined at the beginning of we defined at the beginning of the chapter, to simplify these things. So this gives you a sort of taste of what the automation of defining custom tactics helps you with, because this is a very routine kind of process where you apply multi-step and then you choose some constructor to use in there, and eventually you apply multi-REFL. So what Normalize does is just applies that recipe in a sort of general sense, but you don't need to worry about how that works or use it or anything. Okay, and if I go to the homework again, that's not that. Okay, so that's a fairly long segment, but that's basically how the lambda calculus evaluates and how we can formalize that using the techniques that we've seen in previous chapters.